Okay, hello, we are live. So we are going to start this right now. I'll just share my entire screen. So what we're doing today is CBAS for PETAs. This is a machine learning method that we've worked on for quite a while now. And we're going to just change this to GPU and install all the code dependencies. So this is going to be a lot of code. And I just fiddled around with it. So there might be issues here. But at the end of the day, what we want is protein sequences that are optimal. So this thing right here is a Git repo. Contains a lot of interesting functions and useful stuff, basically. I'm using a lot of the utilities in this file. Not much to say here, but that's that. And then imports, a lot of different imports. By the way, CBAS, if you're interested, is part of this thing by David Brooks. Now, he did his implementation in Keras. Now, I'm not too familiar with Keras, and to understand the algorithm a bit more, I re-implemented everything in PyTorch. So there may be errors. That's why I've been looking over this again, and in fact, I've discovered another error in my implementation. It was actually quite a serious error. It was this line right here, vae0.decoder.predict. So this is kind of clever. vae0 is his prior on sequence space, but ZT, that's not just any ZT. ZT is all the way up here. So for every iteration, you have a fixed ZT. So ZT is this latent space stuff. You draw number of samples is 500. You draw 500 samples of in size equal to your latent dimension. And then you keep that for both your prior, right? To use the decoder for the prior, but also you use that for your current search model. So this ZT is the same as this ZT. I made the two things different. That's a pretty big mistake there. That's basically ruining the whole algorithm. And I think everything else is the same, hopefully. And I hopefully have identified the mistake that has costed me quite some time. So there are utility imports and stuff. Sequence length. So for PETAs is 298. But what we're going to do tonight actually is do it on PETAs. And then also do it on LCC. I have an updated data set for LCC. But right now we're just doing it on this PETAs stuff. Let's see. Yeah, you have a lot of data points here. But some of these, recently we've learned that some of these data points might not be trustworthy. And that actually is like 80% of our data. So that's why we're sort of shifting to LCC, but we're just going to look at PETAs just to make sure the code runs and there aren't any issues here. Why is batch size 100? That doesn't matter. Okay, this is where things get interesting because this is where the PyTorch Lightning stuff comes to play. This is important. So this is a data set wrapper for weighted VAE training. So here's a VAE. Weighted VAE training means that during your loss function, you basically, for your reconstruction loss, it's not just MSE, but you have to reshape your weights, or you have to multiply every input by your weights. And the weights are determined by the CBAS equation, the weighted maximum likelihood. So that's that. I hope it didn't do anything wrong here. That's the reconstruction loss plus the KL loss. I think that's all correct. Okay, so this is a VAE. Let's define that. Model runner. Okay, well, that's the code for model runner. And oh yeah, there was a bug here before that I didn't actually look at that clearly. So this thing with train data loader, oh yeah, here, data set. It needs to be self.dataset because every time you train a VAE, this iterative procedure changes your training data. So this can't be a global variable. In fact, I don't even know why I use a global variable in the first place. It's very dangerous and reckless of me. Okay, so this is run experiment. I am interested in seeing the parameters. So that should have actually, in this folder, there's a simple VAE.yaml. How do I? Oh, I can't drag it here anymore. Usually, oh, here. There we go. Okay. Where am I? I haven't trained the VA yet. So, and this is the model configuration for this thing. Latent dimension is 20. So that's your latent space. Here's a bunch of other parameters. So we do have a GPU and we have a seed. Okay, and sequence length 298, that's fine. So let's just run that. Okay, we are gonna just try training it on Pate's activity. I don't know what this code does anymore. I think we do need to run this. Whoops. Never mind. We do need to run this first to write everything out of FASTA file. Because that's how I coded this interface, read FASTA. Okay. Right, so it reads in a FASTA file. It's called now, where is this? Apparently I'm in CS.ml. Here it is, headers.fasta. These are sequences. Okay, so that's our initial generative model trained on all of these. All right. This was the other idea, that you pre-train on some larger data set. Well, we could try this with LCC. But well, let's not do it just yet. I want to just make sure the code runs. And this was another pre-training idea. You can train on some PFAM domain, but we're not going to do that. Okay. Oh my gosh, yeah, my code is super messy. Right, so these are fine-tuning stuff. Okay, that might be useful later. But right now we're mostly interested in just running the experiment and saving it as a prior. So that piece of code should go right after here. So I need to run experiment, which is this function right here. If model is none, the model is fine-tuned to new. If not none, model is okay. But I'm gonna train a new model here. So delete that. I think yeah, that's the data set. Config I already have. Let's just run it. Okay, so I don't have config. It's too bad. Where is my code for loading in the config? Wow, looks like I deleted it. Okay, I will be loading in my config. It's this YAML file. Here it is. Config fname and then try config blah blah blah. And then that was your prior. So yeah, this is what happens when your code is super messy. Okay, so config is simple VAE.yaml. And let's run this. We are using a GPU. And there's a bunch of warnings about efficiencies. Yeah, it's running fine. We don't need that. So before there was a progress bar, I took that out because I thought it would sort of get in the way of CBAS because you basically have to train a generative model like 50 times. But every time this thing shows up, I was too lazy to figure out how to turn this off. But this is useful. This is the generative model. So it's a VAE, and the encoder has, well, let's say about 600,000 parameters. And then the decoder has about the same. And then at the end, it's like softmax. This is really cool. This is like a text version of your computational graph. But this is running. Very nice. And it should be saving in logs. Yeah, here we go. So right now it looks like we are on iteration. No, it's pretty fast actually. Oh, I think it's done. I think it just finished. There we go. The iteration 49. If you take a look at that, these are the generated sequences. Not a lot of diversity, but you do still see some changes. Like somehow this has a gap character here. Okay, that's fine. So it looks like it's training very nicely, and that's the prior. So now we have prior.pt, which is saved right here. That's the saved prior. Cool. So that's it for our generative model. Okay, well, now we're moving on to the oracle. Set some seeds, define our data set wrapper. This is a really messy function that does the training for us. That's the neural network. Very simple stuff. What the hell is going on here? Why? Okay, that was a good catch, actually. This was probably the result of a midnight debugging session. I probably turned that off because I didn't want the output to be bounded. Yeah. Okay, well, let's turn it off. Okay, I'm turning off the 10H. Well, optimization. So this is an interesting function. Let's not go over the details. Weighted max. What? Oh, okay. So it's already training. Okay, so I don't train the oracles independently. I train it. Well, I declare this function first. And then I train the oracle. Oh, here it is. This is where I train the oracle. Sure. But I am still normalizing. Actually, no, I'm not. Okay, so there are two things that we're predicting: catalytic activity and thermal stability. But because CBAS was doing weird stuff and giving weird results like this, basically what was happening is like the maximum in the data set is like 0.5 after you normalize this stuff. Oh, okay. So I'm plotting mean and variance. And then what happens in the data set? Okay, I guess this was unbounded. Okay, I guess this was unbounded. And then this is the one, this is the maximum value. Okay, man, yeah, well, looks fine. Well, let's just make sure the code runs, and then we can look at it for LCC. Okay. So that was the code running with that bug, bug I just talked about with this. Well, there was a bug where I was like, oh, let's just sample two different things, like for the prior and for the search model. No, you have to sample the same thing for the prior and for the search model, because those are the samples you compute likelihoods under the search model and under the prior, right? That's interesting because in the objective function, there was no log for the prior term, but there is a log here, which is confusing. That's interesting. If you look at the objective function, there is no log there. I can actually open it up because I just presented this thing at a talk. That's the objective function. Where's the log? I guess you don't use the log. I don't know, where is, like, well, if you log everything, it's kind of confusing. If you log everything, this will be the log likelihoods. But in the objective function, there is no log, which is interesting. Well, actually, yeah, that could be something interesting to try. Doubt will change much, but, well, we'll see what happens. So, yeah, I'm acting very nonchalant about this because like, I've been struggling with these things for a while. Prior, okay, why am I pre-trained? Okay, let me just comment that out because I've already trained my VAE. So let's just load in our data set and let the neural network train. Beautiful. I love this validation curve coming down like this, because this says the model is learning at least something, right, before it plateaus. And wow, look at that. Yeah, that's beautiful. So might be interesting to just look at stability then, instead of catalytic, where this is sort of going up a bit. Well, whatever. Let's run CBAS. Right now, you'll see I'm passing in both the thermal oracles and the catalytic oracles. Oh, apparently I'm only doing it for 10 iterations. You should do it for 50. Well, whatever, let's just do it for 10 and see what happens. But even though I'm passing in both oracles, what's happening is, where is what's going on? Yeah, I am not taking the thermal stability oracle. I'm commenting this part out, even though I'm predicting it. I could include this again, but then it'll be sort of unclear which one it's actually optimizing for. It becomes a bit tricky. Yeah, but you could include both of it if you want. Let's just run it. What is going on here? Run. And of course there's an error. Okay, this was one of the things that I just changed. So weighted ML opt, num samples not defined because I just changed that to samples. Good. I think that was the only thing that was off. So, okay. Latent dim is 20. Okay. So the oracle is done training. Now we just need to run CBAS. Beautiful. There you go. It's running. It's running. It's running. Whoa. 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 Okay. I don't know where I'm printing stuff out. Nope. That's not where it is. What am I printing? Oh, okay. Yes, I am printing the weights. So I'm printing out W1 and W2. Each of these should have 500 items because I'm sampling 500 things. So that's why it's pretty large. What's being printed out. But you'll realize that a lot of this stuff is going down to, well, okay. This one's weight is fine, right? By the way, your weights, if you take the log of something minus log of something, that's equal to the log of the ratio, that's the weight. But if you don't take the log, maybe your weights are going to be higher. Because what was the issue with this default weight cutoff? Basically, you say, oh, let's just find where the weights is less than some arbitrary cutoff. Actually, this is 1e minus 6 right now. Find those weights and just delete them from your training data. That's not doing so well sometimes because, well, okay, you see this error? I think that was the reason it's erroring out. You can see how small these things are. And it's saying with n samples equals 0, the resulting train set will be empty. So it's trying to train, well, here, let's expand this. It's trying to train a generative model based on that conditioned subset, but it's not working because the weights are so vanishingly small that you're basically taking away all your samples. Like, look at how small these weights are. So one way around that was you just don't have fixed cutoff, but just remove the lowest 20th something percentile. Another way around that was what was the other way around that? The other way was you had the weights. Oh, yeah, this one is something I haven't tried yet. The log stuff. Why am I doing log? XT is this one hot encoded thing. So this is saying, oh, I want to look at the log likelihood. Right. But what if that's vanishingly small? What if I don't want to take the log? let's just see what happens. This is probably not what you would expect. Oh, sorry, that's not the one I wanted to copy paste. Okay. 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 So I just removed the log for both of these. Run that. So it doesn't change anything up here. It does change the trajectory here. Okay, instead of printing the weights, which is kind of stupid, I'm gonna do plt dot histogram of W1 of W2. I hope that doesn't end up in disaster. Let's run it and see what happens. Weights might just explode. All right. Okay, so here we go. The W1s are near 1. And the W2s are sort of scattered. That's fine. So what are the W2s? W2 is this thing. W1 is that log ratio. So if you look at this thing is W1. And this is W2, which is the oracle stuff. So far, no errors. So this is W1. Okay. So W1 is quite strong in the first iteration, which makes sense. It's not straying too far from the prior. But what's really bad is that the oracle is saying, whoa, 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 your sequences are crap. And is assigning super low weights to some of them, which I guess is a good thing for the oracle. Not a good thing for the generative model. Whoa, okay. Now I can barely even see the oracle, and now the prior is collapsing. Oh no, wait. This is 1E29, okay. So eventually this is gonna go overflow because I didn't do the log. And if you don't do the log, things just might explode. This isn't really representative of anything. Well, you can see the end. At least the first iteration looks fine. This looks reasonable. Like this has a nice strong prior. This really makes a lot of sense because in the first iteration, this is the prior. Yeah, the first iteration R of X is the prior. But what's going on with the oracle? It's disappeared. It has disappeared. Maybe I should plot those two on the separate plots. Well. Okay. This was like a very controlled run. So this one, there's also some other things where you can control the oracle weights to be a bit better than they are here. And that is with this parameter. Right, so sample equals true can be set to false if things start blowing up, because at least what I think, so what sample is, this is their default implementation, by the way, is that you have residue-wise probabilities, that then you sample using this multinomial according to probability P. But this sample is like weird stuff. You can see it even in the, well, I lost it, but even in that initial thing. Oh, let's take a look at this. Well, okay. Well, this sequence, this first number, when was this created? Oh, this was just created. Okay. Oh, just created. That's fine. It looks like it's working. I mean, it's plotting stuff. It's. Let me just go back and see what's going on. It looks like it's on. I don't know what this means. This is because my output wasn't bounded. I wonder if it was bounded in CBAS. Yeah, it's another tab. So let me just switch to the other tab. So let's see, it was build something, or I don't know where the thing was, but it was in here, build pred model. So input to seqlen by n tokens, and then, oh, sorry, what's going on? You flatten the input, you map it to encode 1 unit, and then you map it to H. Oh, sorry, and then you map it to 1. This is also not bounded. So there's no activation function at the very end. There's no 10H thing that's sort of controlling the output. I don't think so. Although I have actually no idea how Keras models work. Yeah, see, this is the really weird thing about like their VAEs. It's like, I have no idea how Keras VAE works. Like you have to specify your loss functions as like these things, callables. Yeah, I don't know. Oh, okay, it's still running. It's getting there. That's a super crazy sequence. I don't actually think that makes any sense. That's an interesting. That's interesting because yeah, I don't know what to make of these results. This is just 5 iterations, man. Oh, wait, hold on. Big brain time. It's really important how you normalize your predictive model. So right now, here it is. I am just taking the log of y activity. Okay. After this run, I would really like to know what was the in distribution maximum? Because if you look at this, this is the data, right? This is a terrible way to view. Oh my God. Oh, here it is. Relative activity. things start to get really wild with these grape sequences. So all of this stuff is grape. And the largest value is like 1,000 something. So if you look at the training curve, or okay, if you take the log, the maximum of that is going to be like 3 or 4-ish. So what this stuff is saying, okay, this is starting to get a little bit more reasonable. But what this stuff is saying is this is 13 order magnitude better than Perez, which is ridiculous. This is e to the 13 times more catalytically active, supposedly, which is completely ridiculous. Let's just align some of these sequences. I don't know what to do. This was with protein solver. You can see how well it aligns, right? These blocks are sort of still consistent. I think what is a red flag is if it has to do so many insertions and deletions for it to do the alignment properly. So let's just, for curiosity's sake, let's just take a look at this first entry. Okay. Sure. The wild type is, I've got this all set up here. Sure, let's submit this. By the way, it's not 2 a.m. It's a Linux time thing that is. It's actually 9:57. Okay, there we go. So as you can see, many gaps. Many gaps. Clearly not really a good idea. Right. Even in the places that are supposedly aligned, well, I guess here, M, T, Y, N, apparently these two things are conserved. Well, this is ridiculous. Might have something to do with the gap character, maybe, because the gap character is never ever seen in the training data. So that's like a serious out of distribution flaw for that neural network. So maybe it's just that. So instead of n tokens 21, maybe let's just change it to 20. Yeah, I mean, even though this neural network does fairly well, it's never seen anything with a gap character before. So, well, whatever. This is almost done running. Well, at least it's not crashing, right? But I think maybe, okay, so the logs definitely matter. And from that first plot, actually, which was quite informative. And okay, the output here is gone. The first plot was basically saying, well, it's good under the prior, which is obvious, right? Like this plot right here. But it's bad under your oracle. Right. Well, let's just plot this. Okay. Sure. Well, this is going to be wild. Oh, really? It's not 1,000 something? Wait, so what? Oh, sorry, I'm kind of confusing myself then about what is this thing. Weights. Okay. So these sampled sequences, this is the weights. This is W1 times W2. Ah, I'm confusing myself. So W1 was W2, and then the second column is the sum of those two predictions. Ah, okay. So I'm sorting, in this case, by weights, which is interesting because I want the sequences that's highest ranked to be those with high likelihood under the prior and at the same time, high likelihood under what? The oracle, right? Okay, well, high predicted function on the oracle. So it was this thing plus this thing. Okay, what's the first thing? Catalytic is the first thing. Oh no, the second one is a variance of the catalytic. That's a variance. Whoa, it's not able to optimize thermal stability as well. Okay. Interesting. I shouldn't say interesting when some of these sequences are just so diverged from the wild type. It's just crazy. Ah, okay. This Q is always here. That's really interesting. I don't know what to make of these results. Because if I change this log stuff, right? If I change this back to the log, the weights are gonna be crazy again because, okay, so let me change it back to log. But I'm gonna say something with the tokens. Wherever I say 21, I'm gonna change. This is crazy. God, it's the mist. Wow, okay. Here we go. This is the beginning of the code. Let's change that to 20. There's no reason why it should be 21. Because the data set I'm training it on does not include gaps. That's going to be kind of tricky for when I do want to do pre-training on gaps, but let me just see what happens if I just remove the gap characters. Okay. I need to change this now from 21 to 20. And this will Load stuff in. That's going to be an error. I know that's going to be an error because in my util file, this is, oh, no, not this one. I define AA as this thing. Now this won't have an error. Okay. Self.encoder. Seems like encoder's dimensions are not exactly the right ones. So, okay, what's happening? You put in through your encoder and it's getting out, one of these is, yeah, okay. So I think I should have reloaded some data sets. I thought I did that. Okay. This is matrix one. Okay, well apparently the input has more dimensions. What's going on? Let's take a look at X then. 212 by this thing. Oh. Get X. I think I know what's going on. This is the stupid thing with loading and importing files. All right. It's just, yeah, whatever. It's just my fault. Because if you, oh, well, sorry for this stupidity that you're witnessing. Yeah, sorry about that. Stupidity that you're witnessing because I'm just, well, that's a quick fix. That's a hacky fix, but it's a quick fix. What you could do then is, well, let's take a look at x.shape again. And that's different. Okay. Here we go. We train a generative model that does not allow gap characters. Forbids it. Saves it as prior. Okay. I wonder if there are any questions in the chat. Well, actually, I don't know. There we go. No one is watching, and there's no one in the chat. Well, okay, whatever. This will be just kept on the channel. I think this is useful information. Let's least the decoding or the debugging part. Although this does take a while, even though this is on GPU. Yeah, let's take a 10-minute break and I'll be back.
Okay. Let's look at this again. Beautiful. Let's just plot it on separate graphs. So I thought plt.hist was supposed to account for like bin size and stuff, but apparently not. So let me just actually print. Let me do this. I think it's. I think it's like that. Hopefully, that's right. All right. Let's run it. Maybe not 10. I think 5 is enough. 5 is enough. Coffee, kiwi here. Mm-hmm. It's the same stuff. But this time I included the log. Dude, come on, man. This is... why was I blanking on this? This is... You guys have been going crazy when you were hearing, oh my god, the log. Yeah, you take the log, and then you take e to the log ratio. Come on. So this is the right one. This is correct. Okay, so this part doesn't need to change. What may need to change is, this will be the next try. I'll change sample to false here, which means it's gonna greedily take the maximum likelihood thing. And then I'll see how the weights change. But I think just even in the second iteration, the things would just go bizarre. Is this a second iteration now? Yes. These are the weights, I think. Okay, well, the hist is nice because it sort of shows us the range. So it's interesting for the oracle, that distribution is similar. Why is... Oh, okay. I see what this means. This is the CDF, the cumulative distribution. So this is like the probability. So this is a really clever line. This is the probability that something is above, I think, y star. Is that right? So yt is the thing you want to look at. And you want to look at some particular quantile. So like, for example, here the quantile is 995. Okay, that might be too stringent. And the weights might just be... Yeah, so actually that's a parameter to change, even though in the CBAS paper, they said this didn't really change much. Okay, and now you can see n samples. It's just vanish. Right. Okay. So let me actually keep the sampling because that's what they do. So let's keep the sampling. And let me turn this down. So 95 percentile is crazy. That's kind of crazy. Let me just relax it to like 60. So if you relax it to 60, the oracle scores are going to be a bit better. There we go. Yeah, I wonder why they said that the quantile doesn't impact it that much. Maybe it was because they were working on such a large data set that even if you do that quantiling, 5% of their data is still 2,500 sequences, because their data says GFP, which is like 52,000 sequences. So 5% is still a couple thousand sequences. So by selecting the top 5%, you're selecting like a couple thousand sequences, which can really then inform your next round of a generative model. Yeah, this is kind of crazy. I am printing traj at 0, which is something. Trajectory at 0 is the max of yt, which is catalytic activity. Okay. So actually, that was how we selected for sequences last time. Which is interesting. Because now I'm selecting it for like, oh, high likelihood under prior, high likelihood under the oracle. You know what? The prior, oh wow, okay. So that was the first iteration, 150 something, skewed towards 1. And basically nothing in the middle. This has been shifted down quite a bit. By the way, no one said you have to do 50 iterations of CBAS to get results. In fact, no one said anything because there hasn't been any experiments on this yet. This iteration is interesting. This is very interesting now. So this is the log stuff, and it's not running out of training sequences. Even in the third iteration. In fact, this is what we need to see. We need to see this thing go up. And we need to see this P come down, hopefully, in the next iteration. Because that's conditioning by adaptive sampling. Right? Because you want higher likelihoods under your oracle. And these weights are increasing. Oh no. Well, it started all at 1. And then something was like 40-ish. Okay. This doesn't really convey that much information. This spiked up a little bit. Okay. This part's interesting because there's sort of this trade-off then, right, between how large this thing can get versus how large this thing can get. This is about, oh, okay. It's important to keep in mind that most of you have 500 samples to begin with. Right, because every time you're sampling 500 things. So this is like almost all of it's around here, which, you know, does make sense, but like this doesn't, how do I know? What that is. Oh, okay. We can try to take it at face value and be like, oh, okay, that's doing pretty well. Okay, it has completed. Wow. So it's a crazy experience. So that was 5 iterations. I think. Where's okay, well, I guess it's 1, 2, 3, 4, and there's no 5. Oh crap. What the hell is this? I might have to retrain it because I had one where there's no gap characters. Yeah. Well, actually, I don't think the hypothesis about the gap character is actually right in the first place. Because what was happening then, let's see, Q is 21. Yeah, let's retrain it with 21. I don't think it's going to affect it that much. I actually do think it's actually the percentile that really mattered. So 21. Let me just rerun all this stuff again. And then you add that gap character back. All right, that changed. And then you update your prior. Okay. I do want to take a look at this thing. Okay, what about this thing? LMENQ. How the hell did it decide on this? Like even the first iteration. What kind of a sequence is this? Oh, let's take a look. That was quick. Yeah, maybe there's something wrong with how I implemented this, but yeah, you know what's happening here? That's the one big difference between this one and CBAS. Shouldn't be that bad. I mean, okay, so the logic predictions, it's getting a bunch of different oracles. Right, that's fine. How many oracles am I training? One. 20. What? No. Sorry. It's here. Oh, okay, it's one. Okay. It's one. Okay, that's fine. That's fine. Okay, that is also fine. This was with gap characters, right? Okay. It's getting late. So I'm just gonna do this with that being false and see what happens in 5 iterations. That's very interesting. By the way, oh, is there a next iteration already? Oh, I didn't stop it. Okay, well, what I wanted to do was increase the quantile to like 95%. But I guess that doesn't make too much sense for our data set. Yeah, in fact, it's crazy enough to sort of even think that you could do LCC stuff with this. Which, that could be a coding session for next time. Because it would be interesting to try out some of the structure-based models. We can save that for next time. Oh, this is done. Yeah, this is not right. This is not right. Oh, you know what might have happened? It's just the decoding part that was being bad. Supplied range of... Okay, so I guess it blew up. Okay, if you stare at this a little bit, right? This is the his tag. That's E, L, S. That might be a mutation, but that's N. Might be a mutation. So it's not as diverged as you think with the gaps. So apparently some weights went into infinity. Is that what happened? It says range of... Okay. Okay, let's include the gaps because we were thinking of like fine-tuning or pre-training on a larger data set and whatever. So if you keep that data set, or if you keep the gaps, then sample is false. Okay, so if sample is false, then this quantile will be 95%. So it'll be at least a bit more controlled here. Oh man, there's so many things that can change here. It's crazy. So many knobs that you can tune. I don't recall seeing something like this. It's just so weird. Why am I seeing that? I guess it's because I set this to false. So that, okay, so this one is the sampled one. And you can see it's quite good. Like what is this, for example? So the generative model is working, like both models on their own, they're working, like no problem. In fact, this is the wild type. Okay. And I'm pretty sure that if you do greedy decoding, most of this is going to just be the wild type. Can you see any differences? Yeah, no, you can't. Oh yeah, okay, that was the thing before. What about this? Okay, that's new generated. That was the last iteration, so okay, let's take a look at that. Wow, okay, that's pretty interesting. You can see how the weights just go down quite significantly. All right. And look, 1e minus 6 is, well, it just keeps going down. Yeah, look at how small these weights are now. So wait, what's the bad thing about this sequence? That their weights are so small. clearly something wrong. That's non-trivial. Right, so this thing is disappearing again. So I tried a bunch of stuff and none of them seem to work. So we're going to revert back to, I guess, at least what seems like was the thing that did work. So you don't sample, right? It's a greedy thing. But basically, just discard, just always discard the bottom 20th, 20%. And forget about the other stuff. Like, yeah, just forget all the other stuff. We can keep the same oracles and stuff, but yeah. Oh, really? Even the first iteration? What's going on? I am where weights is less than cutoff. Weights. What am I doing? Why is this 100? Yeah, so the greedy decoding. Yeah, okay, so I can try this one. You can do the greedy decoding, which is what's happening now. You're doing greedy decoding. And then the next way to try it is the multinomial sampling stuff. And then I think that's it for today. It's very hard, this model, to get it to work. It's quite hard. Okay, well. Okay, I think I can end the stream now, but well, I've never actually visualized these weights before, and this was very instructive to see what the weights were doing and behaving. But I'll show you actually maybe some of those generated sequences. I think this difference in likelihoods, this is the part of the stochastic part. Even though, this might be the same as the wild type. Yeah, I think it might be the same as wild type. It's kind of crazy. Well, then in that case, you should do some sampling. Yeah, as you can see, even in iteration 2, the samples, if you do greedy decoding, it's it's kind of wild. So I will show you what I think. So I guess the whole point of trying out these different things is, trying to see which one works the best. And what I thought does work the best maybe is you have this sampling to be true, but the weights are sort of, not sort of removed by an arbitrary cutoff, but just remove the lowest 20%. And then you run CBAS. This is a crazy ride, actually. It's really crazy because it's sort of bootstrapping itself, like. Now when you do the sampling, you can see how much the oracle detects that this is really bad. So that the probability that something is in the 90th percentile, 95th percentile is mostly pretty low. Okay, this is super instructive to visualize these wastes, but I don't know how good this is going to be. This is as vanilla as you can get, because LCC has what, like 17 sequences? How the hell are you going to do that? Like, I don't see how it's going to do 17 sequences. Yeah, well, we can try. Yeah. This is the irony, right? Your VAE is going to generate some wild sequence, but it's also weighted by the opinion of an oracle who has never seen any wild sequences before. All right, like these things count, like these weights here, they count. And by the way, I think this is going to be fine. It'll be super interesting. Okay, I will make you the promise right now that at least one of these CBAS generated sequences tonight will make it to experiment. Otherwise, why are you even watching this video, right? It's not exciting. But I'm actually going to design proteins. And I've been putting it off and be like, oh, I can come up with a better model, which we are trying to. But ultimately, you do have to sort of just put your foot down and be like, oh, okay. This is as best you can get it with CBAS. Unless there's more code errors, which would be very unfortunate. But let's take a look. Yeah, you can see some of these sequences. Are there differences actually? Let's take a look. So this is iteration 2. Yeah, I expected this to look a bit more wild than this. I'm pretty sure if the weights are this high, let's see, input form. Okay. All right, let's see. Let's see what's happening here. Okay. One mutation. S to an H. I bet that is the Austin et al. Mutation, isn't it? I Am I doing sampling? I thought I said true. Sample equals true, right? 96. All right. That's iteration 3 that just popped up. This is actually a lot more conservative than I remember. All right, that's a lot more conservative than I remember. Okay, and then iteration 4 is out. So let's take a look. Okay. Yeah, okay, this makes sense how the weights just collapsed here because it added this gap character. Wait, this means that's the same. Right. It does contain a lot of repeats. I'm not sure then what's going on because when I say sample equals true, it should be true. Right, for every iteration, you do torch dot rand n. Yeah, okay. So this is interesting. Okay, so apparently this is done. Okay, now let's just plot this and we'll see what's going on. Okay. I guess that makes sense. Yeah, it does make sense. But this is quite weird, especially because now, getting the right algorithm versus getting the wrong algorithm. This might be interesting, right? Now I fix the so-called error, and the sequences are just so controlled. That's really interesting. That was not expected. I thought it would just work better than, because I had errors with that, or not errors, but like the sequence diversity was quite high with that one. Okay, so the CBAS proposed a proline mutation here, a gap here, a valine mutation here, E instead of an A, H instead of an S, which makes sense, and Q. Okay, well, let's download that. Yeah. So, by the way, then, this is only 5 iterations, right? I think the default ran for 50. So that's going to be the next live stream, is to run this for 50 iterations. But thank you so much, actually, in the invisible audience, because without you, I wouldn't have actually done this, because this is kind of a pain to debug and everything. I guess just some notes for next few times. Let me turn my video back on. some notes for next few times is this is a sequence-based model. We're going to explore structure-based models. So eventually, once I figure out how John Ingram wrote his code, I'll be trying out that graph-based neural network. And if I think about it as a sequence generator whose information is conditioned on the graph, then that could be potentially also even used for CBAS. And that is actually a lot more attractive than training on some arbitrary sequence alignments, because you are conditioning on explicitly the backbone of your protein of interest. Then you can even say, oh, I only have 17 labeled data points, which is fine. I mean, you, well, eventually we sort of bottom out somewhere, right? But whatever, we'll see. So in this file, there's some really interesting sequences, I think. You can sort of do an analysis of these mutations. But by the way, this is only sequence iteration 5. Right? You know, obviously those wild sequences won't work. What I was wondering is, what about those sequences that kind of worked? So let me try to show you what I mean by that. So in iGEM, I have some designs already. I think this is from one of the past CBAS iterations. So this was like, wow, May 2nd. So this I was on 19 iterations. And you can see these wild sequences, right? For example, this is CBAS iteration 19. And this was just a vanilla. You can fine tune on Protein Solver. Wow, I actually didn't realize this, but it seems like the sequence samples are pretty much identical. Just the likelihoods are different. So for example, this one is the one that sort of has fairly high likelihood. I think, okay, well, the formatting for these two things was a bit different in this last run. So yeah, I should probably then sort by like the second column if I really want to. But I think right now I'm sorting by the first column, which is the weights of those sequences, right? Well, anyway, there was one. I'll just pick a random one, and we'll see how well it aligns to the wild type. So here's one that is 681. There we go. So instead of that, we have this. And let's see what happens now. Yeah. So crazy. Crazy, crazy, crazy. I am at a loss because last year when I did this, I had some fairly okay and decent results. And the first year I did this, obviously completely different than these designs. I mean, there's some other designs here, but this is crazy. Like, even the top scoring sequence, I guess also according to the likelihood, doesn't align very well. This thing doesn't align very well at all. You can see just how many gaps there are here and there. Wow, okay, this is kind of crazy. You know, it's certainly these are not the ones that we should trust. You know, this is probably the more promising ones. I kind of like this, where this is headed, because this is sort of you can control. Like right now you've got 1, 2, 3, 4, 5 mutations. That's sort of controllable, right? 1, 2, 3, 4, 5, 6, actually 6 mutations. That's fairly controllable, and it's not like a trivial thing that pick those areas, that pick those positions. So I think this is fine. I just need to run this for 50 iterations. Many what do you call roadblocks along the path and along the way. But I think we finally sort of arrived at this clarity in understanding how this works. So we can do it for this. LCC is another issue because it has 17 data points. And well, we'll see if it works for that. We'll then also see if pre-training it on the sequence alignment helps, because I haven't tried it with this updated or this corrected model. So we'll see if it helps. And I think those are the next steps, right? So it's 50 iterations, right? And then look at LCC, and then look at LCC with pre-training, and just see what happens with those. It's not too bad. Oh, by the way, that was at iteration 4 or 5 or something. Anyway, I do have a function that is supposed to let me sample 10,000 sequences. Oops, sorry, where is it? It's using generator as the thing to sample. What happened? What happened here? Okay, well, if you don't let me do it, I will do it myself. So this code right now, what I want is, I have this final generative model. It is stored in this thing called generator, I think. Is it? Yes, it is. It's generator. And then every time you update the parameters of generator. So I'm going to sample 10,000 things from the generator. Yes. And then, yeah, let's just do it. Let's see, get samples. Does this save a FASTA? No. It returns xt sampled. Okay. Oh, is this how you do it? You sorted this by likelihood? Okay, and this was with the prior. Ah, okay. So this was where you did it. Sneaky. Okay, so that's fine. I remember seeing that. Otherwise, why would I be doing that? Okay, so this is over here. N samples. 10,000. Prior, so this would be generator dot sample. Okay, yeah, you don't need the Z's because that automatically does it for you if you don't provide it. Reshape to that, and then you get samples, and then you compute likelihoods, and then you go from highest to lowest likelihood. And this is, okay, be very precise with this. Iteration 4, or iteration 5, it is greedy sampling. And I think that's all the information you need to know. Let's do that. See how fast it is to generate 10,000 samples. Very cool stuff. Yeah, so this is iteration 5. I'll send it to Isaiah, who's on our team, to compute the statistics for this. I assume it's going to be fairly close because there's only 5 iterations. The next time we'll do 50 iterations. And then LCC stuff, we'll see if it works, but if it doesn't work, it's probably better to do that structure-based pre-training. That's going to be super interesting if we get that working. What we're thinking of right now for the structure model is pre-training it on, well, seeing if they have a pre-trained model in the first place. If they have, just get that one. And then that's going to be your pre-trained model. If they don't, then we'll need to train it on a very large data set first. Either we retrain it on all of Cath, which would be a pain. Well, they subset Cath, but like a subset of Cath. Or we can say, oh, the initial the initial training is just going to be, well, ultimately, it doesn't matter what the pre-train is. The pre-train is either the model provided weights or some large subset of Cath. The second stage of fine-tuning, or the first stage of fine-tuning, second stage of training, is on the Cath alpha beta hydrolase domain. Very cool. It's about just under 2,000 structures, something like that. Fine-tune on those. And then you can fine-tune on EC stuff. So you have 70-ish structures that belong to the same, has the same EC number as LCC. 70 something unique structures, I believe, or actually maybe there's some duplicates in there. So for those, you really need to be careful how you do the fine tuning because it can really bias your data if you're not careful. Because with the PTBs, that's the hard thing about the generative distribution here, because you don't know which one works better than the other ones if you just model the sequence distribution. That's why you need that reweighing step. So you generate sequences and you reweigh them, blah, blah. Okay, save FASTA has completed. CBAS, iter 5, greedy dot FASTA. Let's save this and save this. And of course, download block. This is kind of ridiculous because now I have to download this again. How large is this file? Oh, 3 megabytes. It's fine. I'll just send this over. Yeah, thanks so much for watching. I don't know how long this is, but